Great, thank you, Ishan. Our next presentation is innovations in the area of concrete pavements. And this will be given by Dr. Julie Vanderbossche. She is a professor in the Department of Civil and Environmental Engineering at the University of Pittsburgh. Julie?
Thank you, Dr. Zayas, and also to the organizing committee for allowing me to come and talk a little bit about the work that we're doing at the University of Pittsburgh. In all this is about innovation, but innovation is cool. What really is awesome is innovation implemented. And so what I wanted to talk about today was a little bit about what we have done at the University of Pittsburgh. We have a relatively large, well, a large group in the area of concrete pavements. So we're looking at some of the things that we're doing, but I wanted to emphasize the collaboration and the work that we did, because I think that is what helps us get things implemented. But it also has afforded us the opportunity to do some really cool things that we couldn't otherwise do. So I'm not going to focus so much on the science. You can look up the publications and references I provide, but more on kind of the collaboration and why I think we're able to do some really neat things. So the first thing I'm going to talk about is bonded concrete overlays. I worked with the Minnesota Department of Transportation for 5 years prior to coming into academia. And so this was one of the things that I started working on back there. And what you have are thin concrete overlays that are bonded to distressed asphalt. Whether it's an asphalt pavement or a composite pavement where you have asphalt that's been placed on top of a distressed concrete pavement, and then you put a bonded concrete overlay on top of that. So they're thin, they're bonded, and they have smaller joint spacings, anywhere from 3 foot to 3 foot by maybe 12 foot by 12 foot. So relatively small. And by bonding them together, they act as one monolithic layer. So you can reduce the stresses up in the upper layer and get it to perform for a long time, even though it's thin. And also by making the joint spacing shorter than what we might in a conventional concrete pavement, we can reduce the curling and warping stresses. So the idea was to develop a design procedure for this. And again, when I was back at the Minnesota DOT, we built a bunch of test sections at the Monroe Test Facility to look at how these pavement sections perform. And in doing that, we wanted to establish a design process so that we could predict cracking and faulting and incorporate these as a rehab tool within what we do for asphalt pavements. So the problem is kind of a catch-22 thing. You need performance data to have a design procedure. But to get performance data, you have to have these constructed, and nobody wants to construct them without a design procedure. So, you had to get people to do this. And again, it was said something earlier, they're like, well, it's really hard to have people take risk, and being at a DOT, you'll see that, okay, well, if something doesn't perform like it should, you get a lot of calls. So in that 5-year period, there are a lot of calls that would come in at various times, but never in that 5-year period did anybody call up and say, wow, this section, it was a 20-year design and it's 40 years, nice job, right? So there's really not a big benefit either for taking that risk. So it then creates a little bit of an issue. And we had these initial design procedures, one that was originally done by the ACPA Association and the other by the Colorado DOT. And they did these design procedures before they had the luxury of having real performance data. So these were great for giving us a way to get some initial sections constructed out there. And then when we came in, I guess maybe 2010, there were some sections across the country and we could look at how they perform. So a couple of things, you need to have some, I guess, guts, if you will, to go out and construct it. But also you have to remember where it is and that it's out there and kind of keep an eye on it, right? So those are issues as well. So fortunately, we did have these sections across the country. We could look at how they failed. And we found out that they really failed differently depending on the joint spacing. So if we have really small panels and the wheel path lines up in or near the longitudinal joint, you'll get corner cracks. If not, then you tend to get longitudinal cracks where they intersect at the wheel path and the transverse joint. Well, we don't typically design for these types of failures in concrete pavements. That's not what the preliminary design procedures were directly addressing. So we had to go from there. Once we had the luxury of knowing the distresses, we could incorporate that into the design process. Then we looked at faulting, and faulting is what develops when you have differential between your joints and you get water and fines moving around. So you end up getting a buildup of fines on the approach slab and then a void on the leave slab. And so you're driving down the road and you get bump, you know, very annoying. We want to try to design against that. Usually for conventional pavements, they fault pretty much in the same manner. But we found with some extensive data that we had out at Min Road that the joints were developing faulting at different rates. And we looked into it a little bit more. It's like, okay, well, some of them, and this doesn't work, but some of them we have the joints activating through the overlay, where others we'd have it activating through the overlay in the asphalt layer as well. Well, the rate at which that material would pump in and develop these faulting is different. And so we had to figure out, well, what factors controlled what was going on and whether it's going to go through the overlay or the full depth. And so we were able to kind of get some insight into that and develop a faulting model that we're pretty happy with. We just incorporated into the design procedure in the last year or so. But what I wanted to talk about too was some neat things that we could never, ever do without the help of the local agency. So this was PennDOT and a contractor. So we wanted to try to figure out, okay, if we can really isolate some of these mechanisms in our lab, then we could get a better idea for the rate of deterioration. But how do you get aged asphalt into the lab? So we went to the DOT and they didn't just say, oh, you're crazy, get out of here. They're like, yeah, I think we can do that. So they found a concrete section that had asphalt on top of it. And they went out and they marked it up. And then we cut it, the contractor cut it into slots. They milled some of it, left others unmilled so we could look at debonding conditions for both milled and unmilled surfaces. And then they took these slabs of concrete with asphalt on top out of the pavement structure, and then they put it on a flatbed, and then they were able to push the asphalt off the slabs of concrete onto these specialized robust pallets we built and take them down to our lab. That is super cool. And if it wasn't for PennDOT being really creative out in the district, in the contract, I should mention too, this was a overnight rapid construction area. So they were shutting down at 6 p.m. and they had to be open by 6 a.m. And they were letting us do these silly shenanigans in the meantime. So it took a lot of commitment from everybody, but it was really cool, the things we got to do because of them. So we had some lab size specimens, then full scale on the left, the left-hand side, where you have actual 18 kip axle loads being simulated. And we could look at how these joints perform over time when you have fibers versus not having fibers, develop these really cool debonding models. And so we ended up using all this. And then the last part, I think that helps in implementation is provide a tool that can be used, right? Something that makes the technology accessible to everybody. So if you go to pavements.pit or just Google BCOAME, you'll have the design tool. I didn't talk about the technical aspects, but there's a lot of everything is in the technical documentation or training videos in the training toolbox. So feel free to check that out. Another neat thing that I think we do is through this consortium. So it's called Impactful Resilient Infrastructure Science and Engineering. And the idea is that from the time you concept the idea or the need for the research, through developing the process that you're going to address this need, through implementing the research, you keep all parties involved. And so with this consortium, we have the owners, the Turnpike, PennDOT, the county. We have the constructors and the designers all contributing into this process. So they all pay money to be at the table. Again, it's not, you don't want a lot of partners, you want very specific partners. Somebody said, yeah, working with other people that, that are creative and are going to bring that creativity and that energy, that's who you want. And so we have a really good group of partners. They've been doing a lot of good funded research over at Pitt. Dr. Stevens, myself, and the other Dr. Stevens, or Sachs and Stevens worked on this. It was a material compatible repair project. Trying to increase the longevity of partial depth repairs has been a challenge in our area. And I know there's in a lot of areas, whether it's a bridge or a pavement. So this was looking at, we always look at strength and durability, but there's other aspects that might affect this. Do these two materials respond in a similar manner, deform the same, whether it's through an externally applied load, changes in temperature, you get drying shrinkage in your repair material where you don't in the existing. So how can we make this more of a compatible repair material? And so we did some lab work to look at internal curing and matching thermal coefficient expansion, tied that into some fun abacus modeling to look at stresses that are generated to establish some criteria. And now the implementation part. So now we're taking it out in the field this summer, working with the contractor in PennDOT. The other thing is making sure you have the right fix for that repair. So also being incorporated in some work with that Dr. Kasanovich is doing with defining what that boundary area is for that repair material. Is this partial really, should it be a full depth? So not only the area, but the depth of the repair. So that's important as well. Another neat thing that Dr. Kasanovich is working on over there is early opening. So a lot of the I guess kind of the discouraging component of maybe using concrete is the time it takes to cure. And so one way to address this is how much time do we really need? So is this a cutout where you're just letting cars go into a service area? Do you have class 9 semis that are going out here? So what's going out there? What's the mix? How quickly is the mix developing strength? And there's a tool to develop so that you can look at the loads being applied, the time of strength gain, whether you're doing this with non-destructive means through the mirror device, so non-destructively cure maturity, or just breaking beams in cylinders. So this is another tool. If you go to the iRise website, just again, Google Pitt iRise, it'll take you to some of these other tools. And I think I'm about out of time, right? Okay, so I think we have maybe time afterwards for some questions. Thanks again for your time and the opportunity to share what we're doing at the University of Pittsburgh.